Hello Calc 3, welcome back to another video. In this video we're going to be covering section 14.3 which is on partial derivatives. So partial derivatives, when I think back to Calc 3, were I think the first things that I thought of. So to me this section is really where the essence of Calc 3 begins, at least in my opinion. But maybe your opinion will be different at the end of the semester, we'll see. So in this section, we're going to introduce the notion of a derivative for multivariable functions. And unlike the concepts in 14.1 and 14.2, where we gave definitions for limits and continuity, generalizing the derivative to multivariable functions is not going to be as straightforward. There's a little bit more work to be done. And ultimately, for multivariable functions, we perform calculus by holding all but one of the variables constant and then just performing single variable calculus on the remaining variable that we did not hold constant. And when we hold all but one variable constant and then differentiate with respect to the remaining variable, we get what is called a partial derivative of our multivariable function. So let's move into partial derivatives for functions of specifically two variables. So we're going to let f of xy be a function that takes two variables, outputs one real value, and let x naught y naught be a point in the domain of f. So in the diagram that I have here, the blue point is the point x naught y naught. Then consider that the equation y equals y naught gives us a plane that contains the point x naught y naught, and you can think about it as slicing through the three-dimensional graph of our function z equals f of xy. So that plane is this kind of bluish green image that's showing up inside of the diagram here. That's the plane y equals y naught. And then the section of f of xy that's on the plane y equals y naught is a curve. So if we think about what happens to our three-dimensional graph of our function when we cut it with a plane, there's going to be an image that is kind of traced out onto the plane where our function, our three-dimensional function, and the plane intersect. And that image is going to be a curve in the plane. And in fact, we can denote that curve as f of x y naught, because it's going to be the set of all points such that the y coordinate is equal to y naught. That's going to be the domain, and then you're going to have different z values that pop out of the function when y naught is held constant inside of the plane. So the horizontal coordinate in this plane, y equals y naught, is x, and the vertical coordinate in the plane is going to be z. And now we get to the idea of the partial derivative. So the partial derivative of our function f with respect to x at the point x naught y naught is the ordinary derivative, and by ordinary derivative I just mean the derivative from Calc 1 of the function f of x y naught with respect to x at the point x naught. So that's a lot of different words there, but there are some things to recognize. So recognize that if we hold y constant, so we make sure that when we plug in our points x, y into our function, that the y coordinate of the point is y naught, then f of x y naught just becomes a single variable function because we're only changing the value of x, and the output for z is going to change. So again, this is a single variable function, so we can apply calculus that we already know from Calc 1 to a single variable function, which is why the partial derivative is really just the ordinary derivative when we hold y constant at y naught. And to distinguish a regular derivative from a partial derivative, we denote the partial derivative of f with respect to x as del f over del x. So instead of having df over dx, we write it with this funky looking letter like this. So that letter is called del. So del f over del x. And now I'm going to give the exact definition of the partial derivative. The partial derivative of our function in two variables, f of x, y, with respect to x at the point x naught, y naught is, and we can write it as del f over del x, evaluated at x naught, y naught, or just at x naught, y naught, is equal to the limit as h goes to 0 of the difference quotient. So we have f of x plus h, y naught, minus f of x naught, y naught, all over h. So this expression here should look very similar to the definition of the derivative given in Calc 1, where the difference is that y naught is being held constant, and of course we have a multivariable function here. So we have f taking in two different values. And so this is the definition for the partial derivative as long as this limit exists. So if the limit exists, then the function has a partial derivative at that point x naught, y naught. And as you might expect, the partial derivative of f of xy with respect to x at x naught, y naught gives the slope of the tangent line to our curve f of x, y naught in the plane at the point x naught. So remember in Calc 1, the derivative gave us the slope of the tangent line to our function. Well, the partial derivative is going to do the same thing with respect to that curve that's kind of imprinted on the plane y equals y naught. It'll give us the slope of the tangent line if we're only looking at that curve in the plane. So in other words, the partial derivative of f with respect to x at x naught, y naught gives the rate of change of f with respect to x when we hold y fixed at y naught. And here's some notation for partial derivatives just to be familiar with. So we've already mentioned the notation del f over del x, but before we had a line, so it looks something like this, a line and then x naught, y naught down here. We can also write it as this, where we have x naught, y naught in parentheses. This one's pretty important. You can write the partial derivative of f with respect to x as just f sub x. So we'll be using that notation a lot. And then we also have this notation over here. That one won't be used as much. And now we should get into the definition for the partial derivative with respect to y. So it's going to be perfectly analogous, as I've said down here, to the definition for the partial derivative of f with respect to x. We really just interchange x and y here in the definition. So the partial derivative of f of xy with respect to y at the point x naught, y naught is given by, and here we have this notation, del f over del y at x naught, y naught is equal to the ordinary derivative with respect to y of our function f of x naught y, where here we're holding x constant at x naught, is equal to the limit as h goes to 0 of our difference quotient again. So we have f of x naught y naught plus h minus f of x naught y naught all over h. So again, this should look very familiar. This should look very familiar to the definition of the limit from, or the definition of the derivative from Calc 1. And now we want to notice that both of the partial derivatives give slopes of tangent lines at the point x naught, y naught. So I said that in relation to the partial derivative with respect to x. It's also true for the partial derivative with respect to y, but it gives us slopes of tangent lines that are approaching the point x naught, y naught from different directions. So if you look down in the diagram here, the tangent line that's going more from left to right, that's the tangent line corresponding to the partial derivative with respect to x. And then the other tangent line, this one here, this is the tangent line corresponding to the partial derivative with respect to y. And so using the different partial derivatives, we get different tangent lines, and the partial derivatives will give us the slopes of those different tangent lines. And if you look here, notice that we can take both of the tangent lines and we can construct a plane that consists of both of the tangent lines. And a natural question to ask is, if we take that plane that contains both of our tangent lines from our partial derivatives, is that plane going to be tangent to the surface at x naught, y naught? So we have a surface that's formed by our function f of x, y, and if we take the plane consisting of the tangent lines corresponding to the partial derivatives, is that plane going to be tangent to the surface? And this is a question we can't answer yet, but we will answer it towards the end of the video. Okay, so now that we've talked about functions of two variables, let's talk about partial derivatives for functions of more than two variables. So for functions of more than two variables, the same concept is going to apply in that we are going to hold all of the variables constant except for one and then differentiate with respect to that variable that is not being held constant. So let's give an example here. We have a function that takes three different variables. F of x, y, z is equal to x times sine of y plus 3z. And we're going to find the partial derivatives with respect to z, y, and x. So let's start off with the partial derivative with respect to z. So to calculate, we're going to hold x and y constant and then take the derivative with respect to z. So x is a constant, y inside of sine of y plus 3z is a constant. So x is going to remain the same. And then we have the derivative of sine of y plus 3z is equal to cosine of y plus 3z. And then using the chain rule, we have to multiply by 3 on the outside because that's the derivative of 3z. And ultimately we get 3x times cosine of y plus 3z for the partial derivative with respect to z. Now for the partial derivative with respect to y, we hold x and z constant. So again, we end up with x times the derivative of sine of y plus 3z, which is equal to cosine of y plus 3z, multiplied by the derivative of y plus 3z. But 3z is a constant, so the derivative with respect to y is 0, and the derivative of y with respect to y will just be 1. So ultimately, we get x times cosine of y plus 3z. And then finally, the partial derivative with respect to x, we hold y and z constant, and this ultimately just gives us sine of y plus 3z. Okay, now let's move on to a discussion of how partial derivatives and continuity may or may not relate to one another. So we find out, at least at first, that partial derivatives and continuity are not super related. One doesn't tell us much about the other. So unlike functions of a single variable, it is possible for a multivariable function to be discontinuous at a point, even if all of the partial derivatives exist at that point. So remember from Calculus 1 that a function could only be differentiable if it was continuous. But it is not the case that a function has to be continuous for the partial derivatives to exist. We will define the notion of differentiability for multivariable functions below, and once we define that notion, then differentiability will imply continuity at a point. But we want to be clear that the partial derivatives existing at a certain point does not guarantee that the function is continuous at that point. And we have an example here to prove that that's the case. So this function in the example, both of the partial derivatives will exist at the origin at the point 0, 0, but we will find that the function is not continuous at the point 0, 0. So we're first going to find the limit as xy approaches 0, 0 along the line y equals x. And as long as x and y are not 0, then along this line y equals x, we have that x times y is not equal to 0. And because at all of these points x times y is not equal to 0, when we plug those points x, y into our function, 0 is going to pop out because that's we're told that's what happens when we plug in an ordered pair xy such that x times y is not equal to 0. So if we're approaching the origin along the line y equals x, then as long as we're not at the origin, we have that f of xy is equal to 0. And therefore, the limit as xy goes to the origin 0, 0 of our function f of xy along the line y equals x is equal to the limit as xy goes to the origin of the function just 0, so just the constant function 0. And of course, the limit as xy goes to 0, 0 of the constant function 0 is going to be equal to 0. So we have that our the limit as we're approaching along the line y equals x is equal to 0. However, we're given that our function at 0, 0, because 0 times 0 is equal to 0, we're given that our function at 0, 0 is going to be equal to 1. And for that reason, by definition of continuity, f cannot be continuous at the point 0, 0. And now finally, let's look at what happens to the partial derivatives at the point 0, 0. So let's look at the partial derivative with respect to y at 0, 0, and we're going to use the definition of the partial derivative. So we have the limit as h goes to 0 of f of 0 of, I think this actually should be a 0 plus h. So let me switch that here. So we have 0 plus h minus f of 0, 0, all divided by h, and this is going to equal 0 minus 0 over h, because in both of our functions, f of 0, 0 plus h, and then f of 0, 0, the fact that x is equal to 0 implies that x times y is going to be equal to 0. And so our function is going to equal, oh my goodness, that's not even true. Oh, frick. All right, so now that we've talked about functions of 2 variables, let's move on to partial derivatives for functions of more than 2 variables. So ultimately, for functions of more than 2 variables, the same concept is going to apply. So we hold all but one variable constant, and then we differentiate with respect to whichever variable we are not holding constant. So let's see an example of this with a function of 3 variables. So we have the function f of x, y, z is equal to x times sine of y plus 3z, and we want to find the partial derivatives with respect to z, y, and x. So notice that we have 3 different partial derivatives now, one partial derivative for each of the variables. So let's start off with the partial derivative with respect to z. To calculate, we're going to hold x and y constant, and this will give us the derivative is equal to x times the derivative of sine of y plus 3z, which is cosine of y plus 3z, multiplied by the derivative of y plus 3z with respect to z, and y is constant, so the derivative of y with respect to z is 0, the derivative of 3z with respect to z is 3, and so ultimately we get that the partial derivative with respect to z is equal to 3x times cosine of y plus 3z. Now for the partial derivative with respect to y, we hold x and z constant. So similarly to the partial derivative with respect to z, we get x times cosine of y plus 3z. But then when we multiply by the derivative of y plus 3z, the derivative of 3z is going to be 0, because 3z is a constant, and the derivative of y is going to be 1. So ultimately we get x times cosine of y plus 3z. And then finally, for the partial derivative with respect to x, sine of y plus 3z is going to be a constant, so we find that the derivative is just sine of y plus 3z. So now let's move on to a supposed relationship between partial derivatives and continuity, if there is a relationship at all. So remember that in Calculus 1, you found that any function that was differentiable at a point was necessarily continuous at that point. But we have to be careful about making claims like this for multivariable functions. So unlike functions of a single variable, it is possible for a multivariable function to be discontinuous at a point, even if all of the partial derivatives exist at that point. So we are going to define a notion of differentiability later in this video. And once we define that notion of differentiability, it will be true that if a function is differentiable at a point, then it is also continuous at a point, at that same point. But it is not the case that if all of the partial derivatives exist, then the function is going to be continuous at that point. And to prove that to you, I have an example of such a function here. So we can let f of xy equal 0 whenever x times y is not equal to 0, and we let it equal 1 whenever x times y is equal to 0. And we are going to prove that this function has both of the partial derivatives at the origin, at the point 0, 0, but the function is not continuous at the point 0, 0. So first we're going to show that the function is not continuous at the point 0, 0. And to do so, we're going to find the limit as xy approaches the origin along the line y equals x. So if we're working on the line y equals x, then as long as x and y are not equal to 0, we have that x times y is not equal to 0, so that our function evaluated at the points on the line is equal to 0, because that is the condition given up here for our function. And therefore, if we take the limit as xy goes to 0, 0 of our function f of xy along the line y equals x, that is equivalent to the limit as xy goes to 0, 0 of the constant function just 0. And the limit of that function is of course just going to be equal to 0. So the limit of the function as xy approaches 0, 0 along the line y equals x is going to equal 0. However, the function evaluated at the origin at 0, 0 is going to equal 1, because 0 times 0 is equal to 0, and by definition of the function, that means that the function is equal to 1 at 0, 0. And because the value of the function at the origin and the limit at the origin along the line y equals x are not equivalent, this means that f is not continuous at the origin. And now we're going to show that both of the partial derivatives do in fact exist at the origin. So let's start off with the partial derivative with respect to y. We're going to use the definition of the partial derivative at 0, 0. So we have the limit as h goes to 0 of f of 0, 0 plus h minus f of 0, 0 all over h. And because we have f of 0, 0 plus h, if we plug that into our function, we get 0 times 0 plus h is equal to 0. And so by definition of the function, this means that the function is going to equal 1 at any point that looks like f of 0, 0 plus h. And of course, f of 0, 0 is also going to be 1. So this is equivalent to, I should have a limit sign here. Limit as h goes to 0 of 1 minus 1 over h, which is just equal to 0. And then similarly for the partial derivative with respect to x, we have the limit as h goes to 0 of f of 0 plus h 0 minus f of 0, 0. And again, this will give us the limit as h goes to 0 of 1 minus 1 over h, which is just equal to 0. So the limit does exist so that both of our partial derivatives are going to exist at the origin, at the point 0, 0. So here we have a function that is discontinuous at a point, specifically the origin, but it does have both of its partial derivatives defined at that point. Now remember from Calc 1, right after we defined the idea of the derivative, we talked about higher order derivatives, where we take multiple derivatives of a function in a row. And we can do a similar thing here for partial derivatives. So we can take multiple partial derivatives in a row, and these are going to be called higher order partial derivatives. And in this section, we are specifically going to talk about second order partial derivatives. So when we take two partial derivatives of a function in a row, and we have a bunch of different options here as to what these second order partial derivatives can look like, because we have the choice of taking the derivative with respect to x or y both times, which gives us 4 different second order partial derivatives. So the first is the second order partial derivative, where we take the partial derivative with respect to x twice in a row. The second one, we take the partial derivative with respect to y twice in a row. And then the third and fourth are called the mixed partial derivatives, because we take one partial derivative with respect to x and then the other with respect to y. And the order does matter here. So with this f sub xy, we take the partial derivative with respect to x, and then take the partial derivative with respect to y. And with f sub yx, we take the partial derivative with respect to y first, and then the partial derivative with respect to x second. So let's give an example where we're finding the second order partial derivatives. So say we have the function f of xy is equal to x times cosine y plus y times e to the x. And we want to find all of the second order partial derivatives. So we start off by finding the partial derivative with respect to x. So we're going to hold y constant and then take the derivative, and we get cosine of y plus y times e to the x. And now if we take the partial derivative of f sub x with respect to x, we get y times e to the x, because we're holding y constant again. So this cosine y here is just going to go to 0. And we also get that f sub xy is equal to minus sine y, because now we're not holding y constant, so we take the derivative of cosine y and get a minus sine y plus an e to the x. On the other hand, we have that f sub y is equal to minus x times sine of y plus e to the x, because we're holding x constant. And this will imply that f sub y is equal to minus x cosine y. Here we're holding x constant a second time. And then the other mixed partial derivative, f sub yx, is equal to minus sine y plus e to the x, where here we're holding y constant. And notice in our example here that both of the mixed partial derivatives are equal to one another. So f sub xy is equal to f sub yx. And this leads into what is called the mixed derivative theorem. So if f of xy, f sub x, f sub y, f sub xy, and f sub yx, so all of these different partial derivatives here, as well as the function itself, as long as they're all defined throughout some region containing a point AB, and as long as they're all continuous at the point AB, then our mixed partial derivatives evaluated at the point AB are going to be equal. So this is a nice little fact to know, and sometimes it can make calculating mixed partial derivatives easier because it allows us to choose the order that is most efficient for computation. And here's just a quick remark. So we can take partial derivatives of even higher order than the second order partial derivatives. So you just keep taking partial derivatives of the resulting function with respect to x or y. So here's some examples. You could take the partial derivative with respect to x 3 times, or the partial derivative with respect to x and then y and then x, etc. And there would be 8 different options here if we're taking 3 partial derivatives in a row. And now we can move on to the last subsection for section 14.3. And finally, we are going to define the notion of differentiability for functions of 2 variables. And to do so, we're going to use an analog from Calculus 1. So all the things I'm about to say from Calc 1 can be found in section 3.11 in your textbook. But in Calc 1, we found a nice consequence of the fact that a function, say f of x, is differentiable at a point x naught. And you can refer to the diagram as I'm saying a bunch of these different things here. So if our function f of x is differentiable at x naught, that implies that the change in y is equal to f prime of x naught times delta x plus epsilon times delta x, where delta x represents the change in the value of x from x naught to this other x value up here, x naught plus delta x, and delta y is referring to the change in the y value that I have here from our original point x naught to the point x naught plus delta x. And so we can say that delta y can be represented by f prime of x naught times delta x plus epsilon times delta x, where epsilon is some constant that gets closer and closer to 0. It approaches 0 as delta x gets really small. And so in other words, what we're really saying here is that if our function f is differentiable at the point x naught, then the tangent line at the point x naught gives us a really good approximation of our function as long as delta x is sufficiently small. So as delta x gets smaller and smaller, that x naught plus delta x point is going to move down our curve, say to somewhere like here. And now our tangent line is giving us a really good approximation of the curve. And as we get closer and closer to our point x naught, the approximation is going to get better and better. That's visually what this equation here is saying. And for functions of 2 variables, we are actually going to use this nice consequence of differentiability from Calc 1 to, in this case, define differentiability for functions of 2 variables. So I'll just state the definition here. I don't expect to use the definition a ton in this chapter or even in the rest of the course, but I'll state it here. So a function z equals f of xy is differentiable at some point x naught y naught if both of our partial derivatives, so the partial derivative with respect to x and y, exist at the point x naught y naught, and delta z, or the change in z, satisfies an equation of the form delta z is equal to partial x at x naught y naught times delta x plus partial y times x naught y naught times delta y plus epsilon 1 times delta x plus epsilon 2 delta y, where epsilon 1 and epsilon 2 are both going to go to 0 as delta x and delta y get really small. So you can kind of see from this equation here that this is a generalization of the equation that we have up here. We're just adding delta y here, as well as the partial derivative with respect to y. And with this definition in hand, so now that we finally define differentiability of a function, remember that question that I asked way back in the video where we talked about whether the plane containing the tangent lines of the partial derivatives or corresponding to the different partial derivatives would be a plane tangent to the surface given by our function. And here's our answer to that question. So if a function f of xy is differentiable, then it makes sense to say that the plane containing the tangent lines of our partial derivatives, or the tangent lines corresponding to our partial derivatives, is tangent to the surface z equals f of xy. So we finally have an answer to that question. And here's just a last theorem that's probably going to be of use as we move forward in the course. If the partial derivatives f sub x and f sub y of our function f of xy are both continuous throughout an open region R, then f is going to be differentiable at every point of R. So this is a very powerful theorem here. If we have that both of the partial derivatives are continuous throughout an open region, then f is going to be differentiable at every point in that region. Okay, so that's the end of the material for section 14.3. Homework should be up on Blackboard soon enough so that you can get some practice, and look out for section 14.4.